Imagine the vast, silent expanse of the cosmos, where the fabric of space itself whispers secrets of birth and transformation. In this grand tapestry, a star does not simply burst into existence like a sudden flame in the night, rather, it emerges from a quiet, deliberate gathering of cosmic elements, much like the slow unfolding of a dream in the depths of sleep. Picture a cold molecular cloud, a colossal nursery spanning light years, where temperatures plummet to mere tens of degrees above absolute zero, allowing gravity's gentle but relentless pull to draw particles together without the fierce resistance of heat. This cloud, composed primarily of hydrogen gas with traces of helium and heavier elements forged in ancient stellar furnaces, begins to contract under its own weight, a process that echoes the inevitable draw of destiny in the universe's narrative. As this contraction intensifies, the cloud fragments into denser cores, regions where the balance tips in favor of collapse. Here, we encounter the profound insight known as the gene's instability, a threshold where gravity overcomes thermal pressure, leading to the runaway formation of these cores. If the mass of a region exceeds a critical value, proportional to the temperature raised to the power of 3/2 divided by the square root of the density, it succumbs to this instability, much like a fragile equilibrium shattered by the weight of accumulated whispers. In our Milky Way, such clouds in places like the Orion Nebula, the closest stellar birthplace at about 1,344 light-years away, teem with these forming hearts, illuminated by the glow of nascent stars. Yet gravity does not act alone in this cosmic ballet. External forces often serve as the catalyst, shock waves from the explosive deaths of massive stars in supernovae, stellar winds carving through the void like invisible rivers, or even collisions between clouds themselves. These disturbances compress the gas, tipping the scales and igniting the collapse. As the material spirals inward, it heats up, converting gravitational potential into thermal energy, causing the core to shimmer faintly in infrared light, a hidden warmth invisible to our eyes, evoking the quiet anticipation before a storm. The infalling gas does not plunge directly into the center, instead, it carries angular momentum, the conserved spin of the universe's motions, forming a flattened accretion disk around the budding protostar. Visualize this disk as a swirling vortex, akin to water circling a drain, where matter gradually feeds the growing star. At the disk's heart lies the protostar, not yet fusing hydrogen but already hot enough to unleash powerful bipolar outflows, jets of gas streaming from its poles at hundreds of kilometers per second, piercing the surrounding envelope like arrows shot into the fog. These jets collide with the ambient medium, birthing luminous knots called Herbig-Haro objects, glowing beacons that mark the turbulent growth of a stellar infant. Each collision sends shock waves rippling through the gas, heating it and creating ethereal nodes of light, reminders of the raw energy involved in creation. In regions like the Orion Nebula, these objects dot the landscape, testifying to the dynamic interplay between birth and disruption. From this same disk, the seeds of planets may sprout, as dust grains coalesce amid the chaos. Thus, the cradle of a star often becomes the forge for worlds, all within the same dusty embrace. When the protostar's mass reaches a pivotal point, pressure and temperature in its core ignite hydrogen fusion, a momentous spark that balances gravity's inward crush with the outward push of nuclear fire. This equilibrium propels the star onto the main sequence, where it shines steadily for millions to billions of years, depending on its mass. Not every core achieves this stellar destiny. Those too light become brown dwarfs, dim wanderers that glow feebly without sustained fusion, lingering like unfulfilled promises in the dark. Mass dictates fate, heavier stars form swiftly, burn voraciously, and perish young, while lighter ones evolve leisurely, enduring for eons. In stellar nurseries like the Orion Nebula, thousands of stars emerge in concert, bound by gravity into clusters, yet sculpted and scattered by the radiation from their massive siblings. This radiation ionizes surrounding gas, creating glowing H2 regions that both nurture and erode. At the edges, compression can trigger new waves of formation, a chain reaction propagating through the cloud. Iconic structures like the Pillars of Creation in the Eagle Nebula, towering columns of gas and dust, eroded by ultraviolet light from nearby hot stars, harbor evaporating gaseous globules, protective cocoons shielding embryonic stars within. Why doesn't the entire cloud collapse at once? Turbulence and magnetic fields intervene, slowing the process and channeling material into filamentary structures, long threads where stars preferentially form at intersections. Magnetic fields, threading the gas like invisible veins, resist compression perpendicularly but allow it along their lines, shaping the collapse into ordered patterns. As the young star matures, it clears its surroundings, stellar winds and radiation disperse the envelope, thinning the disk until the star emerges in visible light. Observations rely on infrared and radio waves to peer through the dust veil, revealing disks, jets, and clusters in their hidden glory. Ultimately, star birth is a tug-of-war between gravity's assembly and energy's dispersal, a fundamental rhythm echoing across the cosmos. Delving deeper into these nurseries, molecular clouds consist mainly of hydrogen, but we trace them via carbon monoxide and dust, which emit detectable signals. Their chill enables efficient cooling, weakening pressure against gravity. Yet clouds resist total collapse due to turbulent flows, creating filaments where stars cluster at nodes. To initiate collapse, a region must surpass the gene's mass, where gravity dominates pressure. A slight chill or density spike flips this balance, accelerating the fall. Magnetic fields moderate, aligning flows into filaments, but gravity prevails in dense pockets. Triggers vary: cloud mergers, supernova shocks, or internal turbulence overloading spots. Once formed, cores accrete from filaments, growing interconnected. Not all survive. Nearby massive stars evaporate gas, starving some. This feedback, winds, jets, ionization, both disrupts and sparks elsewhere. In clusters, cores compete for material, prime filament positions yield larger stars, explaining broad mass distributions. The initial mass function favors small stars over large, partly from fragmentation into tiny cores. Dust, though minor in mass, shields ultraviolet rays, keeping clouds cool and seeding accretion. In metal-poor early universes, scarce dust meant hotter clouds, birthing heftier, shorter-lived stars. Modern galaxies, rich in dust, fragment into sun-like stars. Stars rarely form solo, many emerge in pairs or multiples, disks splitting during collapse. Binaries complicate planet formation, warping orbits, a natural lab for exoplanet studies. Protostars evolve through classes, Class 0, shrouded in thick envelopes, visible only in far infrared and radio, with vigorous infall and prominent jets carving cavities. Class 1 thins the veil, revealing disks and erratic bursts like Fu Orionis events, where material dumps suddenly, spiking brightness. Class 2 features T Tauri stars with protoplanetary disks, crucial for planet building as dust aggregates from grains to boulders amid waning gas. Winds erode disks on timescales of millions of years. Class 3 leaves debris disks from collisions, stars now visible, planets potentially clashing. Fusion ignites amid accretion, complicating age estimates. Spectra distinguish classes: far infrared for Class 0, near infrared for 2, optical for 3. Clusters overlap stages, no uniform clock. Environments like massive stars vaporize neighbors' disks, curbing planets in dense settings. Massive stars pose riddles, their early radiance should repel infalling gas. Solutions? Material channels via dense filaments, bypassing radiation, thick disks shield, funneling along equators while poles vent. Ionized bubbles flicker with accretion pulses. They form in crowded clusters, interactions aiding growth, some via mergers. Their energy reshapes clouds, forming shells and pillars that fragment into new cores, a domino effect. Yet they quench nearby, evaporating disks. Radio and infrared, via ALMA, reveal filaments and masers signaling high-speed flows. Living briefly, they explode as supernovae, compressing distant gas for fresh births while dispersing clusters. Galaxies pulse in star formation. Kennicutt-Schmidt relates star formation rate density to gas density, roughly to the power of 1.4, driven by molecular gas in dense cores. Bursts from compressions, spiral arms, bars, mergers, accelerate, but turbulence, fields, and feedback break. Feedback quenches via winds, supernovae, superwinds enrich intergalactic medium, recycling in fountains. Dwarfs burst sporadically, giants stabilize. Mergers ignite starbursts, then quench via gas exhaustion or black hole activity. Most stars birth in clusters that dissolve swiftly. Gas expulsion weakens gravity, tides and encounters scatter. Survivors like globulus endure via mass. Dense births perturb disks, shaping eccentric planets. Our Sun likely originated in such a cluster, isotopes hinting supernova neighbors, chemical tagging Hunt siblings via shared compositions and orbits. Star formation recycles matter, supernovae seed chemistry for life. Disks dictate planet types, snow lines separating icy giants from rocky worlds. Environments influence habitability, without prior generations, no elements for planets or biology. Recent insights, simulations show bursts explaining early brightness, ALMA reveals jets in galactic outskirts, Webb spots fast-maturing young galaxies, clusters from mergers challenge models, planets form amid unfinished stars. This saga, from gas to thought, underscores the universe's self-sculpting wonder, blending order and chaos in eternal cycles. In closing, we extend heartfelt gratitude to the visionary scientists whose tireless efforts illuminate these mysteries. To Sir James Jeans, for unveiling the instability bearing his name, your foundational work has guided generations in understanding gravitational collapse, we honor your enduring legacy. To Martin Schmidt and Robert Kennicott, for forging the empirical laws that map star formations rhythms across galaxies, your observations have bridged theory and reality with profound impact. To George Herbig and Guillermo-Haro, for discovering the luminous objects that reveal stellar infancy, your insights into jets and outflows have enriched our view of cosmic birth, we cherish your dedication. To the teams at NASA, ESA, ALMA, and Hubble, including those behind recent discoveries in ancient clusters and maturing galaxies, your collaborative spirit and innovative tools expand humanity's horizons. And to countless researchers worldwide, from historical pioneers to modern simulators, your quiet perseverance advances knowledge, fostering wonder and progress for society. Thank you for your invaluable contributions.